and we started a lot on cavity quantum electrodynamics. Today I'll tell you about a couple of ways that this has intersected in the last few years. So before I do that, I should just highlight the people who did the majority of the work, some of whom might be online. So the majority of what I'll talk about was projects led by a student of mine, Manshil Lin, along with Mohsen, who's my postdoc, whom you just heard, and Saeed, who's a former student of mine who's now postdoc at Texas A&M. And then if there's a little bit of time at the end, I'll talk about another project being led by my student, Boris, which was actually started by a student of mine, Weiwa, who actually the dean knows, right? He's switched mostly to another project, but did in fact initialize some of this work. So under the assumption, based on the previous talk, that I will have to speed up like crazy at the end because you're going to ask a ton of questions, I have an overview here of what I might talk about if time permits. Basically, the idea is confining photons to a cavity lets us to treat them quantum mechanically. That does a lot of interesting things, including mediating long-range interactions. And I'll talk about what that means for out of equilibrium properties, because indeed, as the dean says, I don't do anything in equilibrium, so I can't say anything about that. I'll talk about some older results we have on relaxation, transport, work that actually started with Nathan, who's here. And majority of my talk will be on topological phases of matter in cavity QED. I'll argue that it's a very natural platform to look for topology, and then the project with Boris will be combining these ideas for topologically mediated transport. All right, so big overview of a big research direction in my group, Floquet and cavity QED. So cavity QED is something that's been around for a very long time. Floquet is something that's been around for a very long time, periodically driven systems. But usually these are talked about as fairly different fields. So I'm going to argue they should not be exclusively thought of as such. And to get us there, let's start by just discussing a little bit about tradition. So time periodic drive or Floquet drive is a very, very useful tool for engineering a wide variety of quantum and classical systems. So here's a classical Floquet system known as the Kapitsa pendulum. It's a regular pendulum, and then if you start shaking the pivot point up and down very fast, pendulum inverts. You get a new stability. The dynamics or the equivalent kind of equilibrium behavior is quite different than the end-driven system. The math under the hood of why this works is Floquet's theorem, which says that if I have a time periodic Hamiltonian, I can decompose the full evolution into two pieces. One thing that looks basically, that should be a little T, apologize, like a static Hamiltonian, and one thing that looks like a time periodic piece called the micromotion. And this should look very familiar to, I think all of you have done condensed matter. Even I have, even though I didn't work on it. This looks like Bloch's theorem, right? So Bloch's theorem, I have a periodic lattice in space, and that decomposes my wave functions, my energy structure, and so on. And in the same way that I can mess with this Hamiltonian and Bloch's theorem to get all of the band structures and the heart of what we know how to do, I can mess with drive to get all sorts of interesting phenomena that are captured within this, this piece of dynamics here. So primarily, this research has focused on using that to manufacture this HF right here, the effective Hamiltonian, the Floquet Hamiltonian. We usually call that Floquet engineering, and it's a workhorse of AMO and condensed and even now modern condensed matter physics. So for example, the so-called flux lattices, the effective magnetic field on neutral particles, use Floquet driving, solids in both the superconducting qubits, this is called atoms. Whole host of other things that I've decided not to include here. What I would say is that's great, and definitely we have a lot of papers thinking about what you can do there. What is somehow more fundamentally interesting to me is to actually not care so much about the static Floquet Hamiltonian and to talk about the micromotion piece of the puzzle. And the reason for that is this is now fundamentally non-equal. In principle, anything I could do with a flow K Hamiltonian. I could have done with a static Hamiltonian if I had enough control. It's an engineering problem. As a physicist, I'm interested in this thing that you can't do without time dependence. The periodic phase, the micromotion, is fundamentally non-equilibrium. And I think most of the most interesting flow K physics out there comes from that. So the example that was hot a few years ago is time crystals, which is a very fancy way of saying go up and down. But anyways, it spontaneously breaks trine translation symmetry. It is now established as a clean phase of matter, and that is a micromotion piece that is asking about what happens within a cycle. There are a lot of other implications of this, one of which is about topological phases that I'll talk about today. And so that brings us to cavity QED. Flow K is fantastic. We know how to do a lot of things with it. There's a whole host of literature on this. And mathematically, all the time we talk about it as if this drive laser is some quantum thing, and I'm going to absorb energy. I'm going to absorb photons from the drive. Lose energy, I emit photons to the drive. So, and there's in fact a whole mathematical framework of this called the extended zone treatment. A few years ago, we started down the path of just taking this analogy very formally. Okay, so we have a flow K system. We're just going to formally treat the drive laser quantum mechanically, and it's not crazy because that's exactly what happens in cavity QED. You basically confine your photons so they're long enough lived, and for us, infinitely long lived, such that you have to think of them as quantum mechanical degrees of freedom. And so every flow K system that you know and love gets mapped to some model in many-body cavity QED. And then we ask the question, given such a model, with some interesting flow K physics that it came from, what's going to happen on this side of the equation? Hopefully I'll convince you today is actually some fairly non-trivial things. Before we get there, just a little bit about cavity QED. So this is a very well-established field. There's a lot of work that's been done in few body cavity QED. Many bodies, maybe a little bit more recent as a active field. The primary use of cavity QED historically is to enhance light matter coupling by just basically making those photons bounce around for long enough that they can do something meaningful to your atoms. That's quite. Go ahead, please.
Basic question. So you have this time periodic drive, and then you kind of quantize them. So where's the periodicity of the drive in which property of the photon inherits the periodicity of the drive?
I don't know if that's quite a well-posed question.
Yeah,
what I can say is there's an incredibly trivial thing that you do. Apologies to the people online won't be able to see this.
They will.
Oh, they will?
Yeah.
Oh, you have fancy.
We're very
Fancy how? Might not be able to see it. It might be a little bit chalk.
We buy nice food outcomes for free. Look, I can even.
So everywhere that you had an e to the I omega t in your drive, coupled to some component in the Hamiltonian,
On the light.
this becomes effectively, let's say, the Heisenberg picture of question of just the coherent state. And so it's as trivial as this maps to, let's say, an annihilation operator, depending on my choices. Convention. And then I do the same thing with the Lewisian conjugate, and then I add my cavity. And you can show, you have to be a little careful about the coupling constant here because square roots of n's that are floating around, but other than that, these are formally identical problems and an appropriate semi-classical. So that's it. This dynamics is inherited in the dynamics of it.
So if you're using a flow K drive or a not flow K drive, it doesn't matter for the properties of the photons.
No, you need a flow K drive in order for this to be a well-posed method. If I have a random drive, something with no time periodicity, then if you like, I could probably map it to some multi-mode or infinite number of mode, cavity structure, but then you don't get anything particularly small. The fact that it's periodic, the fact that it's a single mode.
Oh, I see.
Yeah.
That frequency is the mode of the drive.
And that frequency is the frequency of the cat. Exactly. How much energy it costs to put it on.
Yeah, that's.
Good. Thank you. Okay, so enhanced light matter coupling is what we mostly care about. That's directly related to the fact that this is a very, very valuable measurement tool. In fact, it's used in quite a few, about most precise measurements out there. Probably what's most interesting today is this also allows you to modify the interactions if you have multiple particles in a many-body setting. And the idea is very simple. You know, you have two, let's say these are superconducting qubits, but it could be atoms coupled to the same cavity. And they can exchange energy, or you can create, say, a virtual exchange interaction by having this guy flip, emit a virtual photon. That virtual photon propagates around this global cavity, gets absorbed by the other guy, and they share infinite range flip-flop interactions. And I added this, apologies, right at the end of the last talk. This isn't just, you know, speculation. It's been done, and it's actually been used to realize another route to supersolidity. This is this paper from 2016. It's a different type of supersolid. It's bad for you, I think, because it's just a breaking of discrete symmetry. So it's I feel like it's a discrete charge density wave, but it is a different route to supersolidity, which also kind of comes from a long-range interaction here mediated by the cavity. And perhaps there's something in the medium that we might get to by the end of the talk, is I'll think about more interesting structured cavity modes. They might do something fun and in between. Anyways, that's kind of fun. Okay, so confining photons to a cavity makes a many-body cavity QED. That mediates long-range interactions, and there are three things that I might have time to talk about. One of which is out of equilibrium. This is going to, oh, I think I already did this slide. So here's the transport. Here are the two things I'll mostly talk about. Let me just quickly flash through some of the older results that we have on non-equilibrium behavior here. So you imagine you have this cavity QED set up, many-body interacting with long-range interactions mediated by the cavity. What happens out of equilibrium? So generally in the field of non-equilibrium physics, the most obvious thing to look for is thermalization. But we certainly know a lot of routes out of thermalization at this point, one of which that we've studied a lot is many-body localization. So here you have a strong enough disorder that it outcompetes the long-range interactions, basically in whatever initial state you put in, there's memory at that rate times. So you can ask how this would work in the context of cavity QED, and it's really not at all obvious. So flow K would tell us, well, this is just a formal mapping that I can prove mathematically. In flow K systems, up to pre-thermal stuff that I won't talk about, there is localization that is possible. On the other hand, if you think of this as some infinite range interacting model, we know that that is supposed to kill localization immediately. And so it'll become arcodic, ideally thermalizes, that that's actually not something I'm gonna explicitly claim. And this tension took a little while for us to resolve. This is the project that Nathan led back when he was in Berkeley. And basically the conclusion we came to is it depends on the order of units. So if you basically pump yourself up to a semi-classical regime where the photons act truly classically, so you have so many photons, it doesn't matter, n plus one, then indeed you get kind of a flow K thermal to MBL transition. As the photon or whatever central particle comes down and behaves more quantum mechanically, it notices that it's quantized. Generally speaking, the MBL phase gets lost. And all that you're left with is something, I don't really want to claim thermal, but at least ergodic. And we have, go ahead.
Is it like a
Oh,
1D or one dimensional?
It's one dimensional that we simulated. Right, so I would say 1D is the only thing that even this is probably possible for, because there's a ton of evidence that MBL is just dead in the water above 1D. Though I will say that my only claims will be within what you would call the pre-thermal MBL regime now. And I think you can do that in 2D too. It's just maybe not even as long as 1D. We won't make such long time statements for the most part. So I'm just going to be kind of a little agnostic to that. And keep in mind, it's 1D before you have the cavity, but then the cavity kind of makes this 1D into a infinite or zero dimensional model, depending on how you put it. Creates this kind of star lattice. I don't know, whatever that thing spoke. Okay, so if you accept that as true, it has a lot of consequences and really unusual things can happen. One of which is it inverts the conventional mobility edge story. The idea being that your highest energy densities is where the photons look most classical. That's where localization is possible. The lowest energy densities is where it notices it's in a cavity. That's where thermalization is possible. So as you increase your temperature, you localize. And we have some pretty good numerical evidence for that in a handful of models. Another one is, despite the fact that this cavity is long range and you kind of think destroys localization, it can also induce it. Because what can happen in the strong coupling limit is you form these kind of global polariton type excitations. And now when a particle wants to move, it has to drag the cavity with it. And you can basically argue that that kills tunneling. It's the quantum variant of coherent destruction of tunneling, but it has slightly different behavior and actually works even if the cavity is not in the semi-classical. There's this really fun project that Boris has been working on disorder enhanced transport. The idea being that because this is a long range mode, it can actually allow you to transport energy over infinite distances in principle. And normally disorder is going to, screw up transport because it Anderson localizes the particles. But once you've Anderson localized, this infinite range coupling actually turns on in a much more effective manner. You get less destructive interference of that infinite range behavior. And you get this enhancement of transport, which other people have found before us. We have some slightly new models that we're cleaning up to explain this better. And then finally, something I'll just flash up, which we don't understand yet, is what about if you have loss? The simplest form of loss here is the cavity can just leak photons. And if you do that and you go to the steady state and you look at temperature fluctuations on every site, you see this really interesting thing that temperature fluctuations relative to average temperature become order 1 at low interaction strength. Don't worry about the power law here, that's not so important. But then as you increase the long range coupling, the thing that can thermalize you, it actually goes down exponentially with system size. And this has been seen in other models as an indicator of a MBL-TTH transition. Then as you ramp up the dissipation, it actually becomes more localized, if anything. So an increasing system size, my thermal fluctuations go up, suggesting that dissipation doesn't immediately destroy localization, or at least there's some signature of non-areas. All right, so that gives you some sense of the many body physics that we want to do. That is perhaps more controversial because most of it is in incredibly teeny system sizes, numerics, but at least we have some claims. I'm going to tell you today about what I think is a much less controversial story, but also quite interesting on topological physics in these settings. And in order to set up that story, I need to say a little bit about topology and flow cases. So people know about topological physics. It's really exciting. How is it different if I drive my system? The canonical example that tells you something's going on is this thing called a pi Majorana, which is basically the same thing as a conventional Majorana. So this is a band structure of a conventional Majorana. You have the superconductor, you have the particle hole bands, and then there is a solution that is its own particle hole conjugate, which is this so-called Majorana 0. Setting aside experimental issues, this is something theoretically we know is absolutely possible in good diagrams. The reason there is only a 0 mode is because particle hole symmetry demands for you that any solution that it's a Majorana has to have E equal to negative E. As soon as you drive, you've lost energy conservation, and so you only conserve energy modulo absorption or emission of photons, H bar omega. So there is another solution to this equation, which is energy is equal to omega over 2. And that is pi phase per cycle. That is the so-called Majorana pi mode. And superconductors with a pi mode, that's a fundamentally different topological phase than superconductors with a 0 mode, which may be interesting, may be useful. Let's just say it is different. You can go through a whole exercise of constructing a periodic table, stolen from Moy and Harper. And indeed, it is bigger more interesting than the undriven system. This is even without interactions. Today, we're going to examine one particular class on this periodic table, which is two spatial dimensions with a flow K drive and no other symmetries in class. And what I'm going to tell you is this has a natural realization in cavity QED. It has some very interesting topological pumping properties, and I will propose a route to realize this in what I consider to be realistic experiments. All right, so before we get there, we need to talk about the traditional variant of this two-dimensional driven system, which has a name. This is known as the anomalous flow K instead. This is a two-dimensional system that has edge modes in both the 0 and the pi gap. So these you can think of as winding around the flow K Brillouin zone in an imperturbable manner. Can't get rid of that without closing one or the other of those gaps. Now, one of the beautiful things about this is there's this really nice model from Rudner et al. More than 10 years ago now, that realized this in a completely trivial flat band system. The idea is as follows. It's a 5-step flow K drive. The first step, you turn on these red bonds. The second step, you turn on these blue bonds, and so on and so on. And if you tune it on just long enough to induce a single tunneling event, you can just trace what happens to the particles. They hop to the left, up, right, down, and they come exactly back to where they started after a flow K cycle. And then you add some disorder for D2. When you map out the energies of that, the flow K Hamiltonian, the thing that people always love, is 0. That's your flat band there. And the only interesting thing that happens is the micromotion. These edge states come from the micromotion. That happens because it hops to the right, then it tries to hop down, but there's nothing there. Then it hops to the right, then it tries to hop down, but there's nothing there. And you get chiral edge states, despite the presence of this trivial, very localizable pull. So that inspired us to think about realizations. Maybe I should quickly also say this has been realized in cold atoms. This is Monica Adelsberger and company, and they see edge transport. But it inspired us to think of realizations using this common technique known as dimensional reduction, which is basically you just take one spatial dimension, take its momentum, and you just replace that by a 2D parameter. So the familiar example of this is the 2D Chern insulator, so the integer quantum Hall effect. You replace one momentum by a tuning parameter, you get a Foulis charge bond. When you do that in this context, you get a phase of matter that we call, what do we call this? The flow K Foulis energy bond. There it is. Which looks like this. So it's a very, very similar idea. This is literally that square lattice model, except now, instead of hopping up, I just pick up a phase factor on my hop, e to the I left. And the band structure looks exactly like the AFI, but it has this really nice property that now it's going to do something very fundamentally different. It's going to pump energy. And the way to see that is to look at these edge modes. Let's say the blue edge mode right here. When I undergo an adiabatic pump of lambda, starting from 0 going to 2 pi, everything comes back to itself except my quasi-energy, my energy mod pi, mod omega, is increased by 1 photon. I've absorbed a photon in the trap. And the right edge simultaneously emits a photon in the drive. So there's energy pumping that is quantized in this. We studied that. There are some very interesting things I could say. I think I will skip through that. But the one part that will be important for what I'm going to say is what happens if you don't just adiabatically ramp, you do this kind of fast. So I ramp lambda, but I do it at a scale that's commensurate with the original flow K drive. Not commensurate, incommensurate with, but of the same way. Naively, that would cause heating problems, but it turns out actually it makes the system better. It's a much more well-defined, much more stable phase of matter, which we call the quasi-periodic flow K Foulis energy pump, or QF tech. I think I took the whole thing on here. It's a little hard to see from this plot, but if you go down to really, really low frequencies of driving, which is like the adiabatic ramp, no matter how much disorder you have on your system, the system actually stays delocalized in photon space. And it actually, this trivial phase kind of permeates into here. As soon as you add a little bit of incommensurate driving, you get a reemergent topological phase, which is much more stable. And we were able to show that that works. It's very nice. So the reason that you need that additional increments or drive actually comes down to what the photons are doing, frequency space localization. So to get there, what you do is you take your Hamiltonian, you write it as two drive frequencies, which I could also just think of as two phases of the drive, phi1 and phi2. And for the moment, imagine that I could write down the flow K eigenstates of this drive, some generalized flow K theory, which I'll call U. If I could do that, then it turns out you can write down this micromotion unitary, which is basically just starting out with some initial value of the phases. It's telling me how it gets mapped into the micromotion. And because these guys are defined 2π, these are compact. Is defined on a closed surface. The other thing you have to do is you have to take your spatial dimension, you have to turn it into a compact parameter, so you can do that by twisting boundary conditions, for example. That's this capital phi. So you have a three-dimensional unitary object that is defined on a compact on a 3D torus. That defines a winding number invariant, and it turns out this is the winding number that you measure as your topological invariant in these systems. Now, the issue is actually at step one. Assume we can define localized eigenstates. That turns out to be a non-trivial statement. For a single frequency flow K drive, this is always possible. That's the statement of flow K's theorem. That's why the AFI is always defined in flow K. As soon as you make it bichromatic or multichromatic, it is no longer guaranteed that these things will be localized in photon space. And so the way to see that is you do exactly this mapping that I just mentioned. Your e to the I omega t's become this new emergent photon degree of freedom. Now I have two drive modes, so I have to have two cavity modes, omega 1 times A1 dagger A1 plus omega 2 times A2 dagger A2. And then they couple to your Hamiltonian via these terms. So basically the Hamiltonian now causes transitions between the different photon number states in this extended zone picture. And one direction of localization is trivial because these two terms now look like an electric field in photon space, right? They're creating a tilt of your chemical potential along the n dot omega direction. So just from energy conservation, you're going to stay localized into a plane that's perpendicular to this. This is called Wannier-Stark localization. But then within that plane, it's not so obvious. You have an isoenergetic surface. The key point is, as long as these guys are quasi-periodic, meaning I take an irrational cut through that lattice, I roughly speaking get a quasi-periodic potential, and that can admit quasi-periodic localization. But only for certain irrational numbers, only for certain Hamiltonians, and that's the thing that we have to make sure of if we're going to have a well-defined topological basis. So that is what we established. Question, yeah, please.
Yeah, so this quasi-periodic cut is like an Anderson localization of this direction in 1D or?
Right, I mean, you should be careful. Anderson localization is true disorder. This is almost a quasi-periodic potential because it's periodic in 2D. But then when you take an irrational cut on a regular lattice, you get a quasi-periodic. It's very much like the potential that you have in an Aubrey-Andre model. Now, that's not quite accurate because it's actually smeared out over the Wannier-Stark localization line. Huh?
It's more like a Fibonacci quasi-crystal.
I would say it's more like an Aubrey-Andre model, which is a little different than Fibonacci quasi-crystal by my understanding.
Yeah.
But it's anyways, it's an incommensurate potential, roughly speaking, added to your photons, and then you have to ask if that incommensurate potential is sufficient to localize, which is there are mobility edges in the system, so it's not like usual 1D models that are automatically localized. Anderson, if I had a one-dimensional cut and have a real disorder, I would be guaranteed to localize. So that's a key difference. Does that make sense?
Yeah, but in Fibonacci there is no localization. That's right.
So it's not. That's why I'm
Okay.
so it's not that. It is more like Aubrey-Andre where there is a transition depending on the strength of the potential, which is set by the matrix elements they have itself. Okay. Good. So we have established that we've shown localization in these systems, and then we started to ask the question of, how could this be measured? So it turns out this is an energy pump, as I advertised. If you think about what that means in this bichromatic context, now what's happening is you have a 1D system and kind of fluctuations at its edge are pumping from one of the drive photons to the other at a quantized rate, which is like h bar times the product over 2 pi. You can then do one further dimensional reduction, and maybe this is going to be easier to do experimentally, to now have 3 drives coupled to a 2-level system, finite level system. And then that pumping should become pumping between these 2 drives that is mediated by combined cavity qubit system. So that's the thing that I'm going to tell you most about today, is this trichromatically driven qubit. We studied that in this original paper, and I should also say there's a parallel work by Anusha's group at the EU, where they studied a very similar model, and they found topological phases of matter. We have different phase diagrams, we have different models, but in every case, you could get a nice topological response function. So why am I telling you we need to study this? Well, it turns out there are a few problems. One is that measurement of either of our proposals might actually be really hard to do, because we didn't actually say how you would do it. The second problem is both of our driving protocols, if you read the fine details, are complete experimental nonsense. Our proposal had these coupling of the qubit to both photons at the same time, which is very hard to do if you talk to experimentalists. Theirs involved counter-diabatic driving. And if you Fourier transform counter-diabatic driving protocols of a step function, you get arbitrarily high, like 8⁵ times sigma plus terms. And every order, really. So these protocols involve terms that are never going to be realized in experiments. So I set Mancho on the task of was to come up with something that's more physical and to discuss how we could actually measure this in experiments. And after some work, we came up with what we think is a very, very nice protocol to realize this topological phase. The protocol is inspired exactly by this Rudner picture of the 4-step drive. The idea is here on a photon/spin lattice. So here's N2 photons, here's N3 photons, and then up and down are the 2 spin states. You basically are just going to try to come up with these, in this case, 6-step drives that enclose a loop exactly. So here, for example, I flip the spin, so it's a sigma plus term, at the same time as losing a photon from N3. Then I jump to here, then to here, and then back. You can kind of see this looks pictorially quite like what was happening in the Rudner model. And the nice thing is this is actually a 3-step drive, and then you run it for 2 cycles. First off, it has a winding number. It does exactly what I said it should. You repeat the cycle twice, and you actually loop around 2 unit cells if you count carefully. So it should have a winding number of 1. And these models right here are actually quite nice. I don't think I go right to that. This is what's known as a Jaynes-Cummings interaction between the qubit and the photons. This is known as an anti-Jaynes-Cummings interaction, and this is just driving the qubit by itself, which is much, much more reasonable than any of the nonsense that we had in our earlier videos. All right, so before I explain how one could realize that, let's talk a little bit about topological pumping. Let's see if it has a phase of matter. Let's talk about pumping. There are 2 different ways of looking for topological pumping here. Let's say the easiest thing to do is to go into the bulk of the photon lattice and look for whether or not it's enclosing these little loops. That's formally quantized as this thing called a magnetization, which is just basically measuring like magnetization loops. We calculated that, and we found that indeed it's quantized. So before doing that for the photon problem, what we did is we kind of went backwards to the Floquet problem, the 2 periodically driven Floquet problem. Wrote down this magnetization. Technically, it's traced, so you actually don't have to worry about your initial state. You average over initial states, and lo and behold, it works. So this is this magnetization that I promised you should be quantized as a function of time. After some transients, it plateaus at 1. If you plot out a phase diagram of this, there's beautiful topological phases that emerge as a function of these 2 drive frequencies. There's some interesting stuff that happens near the phase transition, which is related do delocalization and commensurate potentials is actually quite interesting. And then trivial phases if you don't drive like you want to. So this model, very simple, but it does have a well-defined kind of clean topological phase. Now with that warm-up done, we went back to the photon picture, which is probably the most interesting case, trying to see if you can measure pumping between photon degrees of freedom. A little bit more challenging, but indeed we can. So if you drive it at too slow of a frequency, kind of looks like it wants to topologically pump, but then it does decay out. Long times you can kind of see this curve doesn't seem to saturate at 1. You have to drive a little bit higher frequency, and then you get these nice topological pumping saturated. So that's very similar to what happened in the 1D case. It's kind of, you need reasonable frequency in commensurate drives in order to stabilize a phase of matter here, basically because you need this 1D Stark localization and the perpendicular localization to happen in flow space. But we've been able to see that you get kind of a disgusting looking, but with a well-defined topological phase diagram here. And if you want to see something that looks a little prettier, what you do is you change the coupling constants. You park yourself at a given frequency, now you change coupling constants. That gives a much prettier looking topological phase of matter, where we can now here very clearly see that when you go outside of this red bubble, which is your nu equals 1 topological pump, to something topologically trivial, there's this region right here where it delocalizes. So the way to see that is you actually, you just take your wave function, you time evolve it, you Fourier transform the wave function itself, and analyze basically the spectrum of Fourier coefficients. It's like frequency space localization. So if there are a few Fourier coefficients, that's localized. If it's dense in Fourier space, that tells you it's frequency delocalized. And you can immediately map that to something like a participation ratio, and you can see this kind of ring of delocalization is your topological phase transition. Pretty clearly. Okay, so there's a topological phase of matter for this very, very simple model. It's stable. We know where we have to be in parameter space. How close is this to experiments? Well, the first thing, as I already said, is these are not crazy terms that we've come up with. It's either a Jaynes-Cummings or anti-Jaynes-Cummings interaction, or just direct qubit drive, which definitely people can do. If you talk to people in the cavity QED literature, they would say this is easy statically. So Jaynes-Cummings is kind of a canonical thing that happens when your cavity and qubit are very close to resonance. Anti-Jaynes-Cummings is less common, but we actually don't have to worry too much about that, because what we can always do is we can simply dump a pair of pi pulses around the x-axis in front of or behind this guy to turn the anti-Jaynes-Cummings into a Jaynes-Cummings, because you're just flipping your qubit before you go. But time-dependent Jaynes-Cummings with multi-mode cavities, that's actually not something that I have seen in the literature. And if you know that I'm wrong, then please tell me, because we're about to claim that we have this nice protocol. If somebody knows a better one, at least my friends who know cavity QED didn't. So yeah. So that's the next thing we set our minds to, is to try to figure out, is this possible to do experiments with these tunable time-dependent Jaynes-Cummings couplings? And there are 3 protocols that we've managed to come up with, which we all think have potential. The first one is, in principle, very easy. You just tune the frequency of your qubit, because the way Jaynes-Cummings happens is basically there's a resonant energy transfer between the qubit and the cavity. And so if you can just tune your qubit into resonance with the cavity that you want to couple to, you get Jaynes-Cummings pretty much for free. So first I tune it in resonance with number 2 and with number 3, and that realizes all the terms that I would want in my Hamiltonian. It turns out that's something experimentalists tell me they don't like. I just think they're lazy. They're any on the talk of it. It seems like this leads to some heating issues, some crosstalk issues, but if you dig in, there are certainly groups that have shown this is in principle possible. So that would be the easiest way of doing this. But let's accept that they tell me it's very hard, and see if there are other ways to realize a time-dependent Jaynes-Cummings or anti-Jaynes-Cummings term. The second option we were able to come up with is a 2-photon resonance term. The idea is as follows: you drive somewhere between the qubit and the cavity that you want to couple to. So it doesn't resonantly hit either of them, but now if I absorb 2 photons, that can emit as one cavity excitation plus 1 photon excitation, so that's the anti-James Cummings. And the problem with this is it is some higher order perturbative process. It requires 2 photons from the drive plus 1 photon coupling to the cavities. So it works, but it's really slow. That said, it might be doable within experimental settings. So I want to mention that. That said, the best protocol we can come up with is actually what I call an amplitude resonance. And this is a much lower order perturbative process. The idea is now you're going to do the usual thing you would do with the qubit. You drive it on resonance with the qubit from some classical light, but you drive strong. And specifically, you tune the amplitude of your drive such that there are flow case sidebands that are resonant now with one of the cavities, the one you want to couple to. So the way to see that this is going to do what we want, first off, you go into a rotating frame with respect to the drive, which basically makes the qubit degenerate, qubit degenerate, and now replaces the photons by their detuning basically from the drive laser. And now these are degenerate, but they're coupled by the drive with this Rabi frequency that creates a new basis, the X basis, where it's gapped by the Rabi frequency. And if that's commensurate with your photons, now you get James Cummings interactions in the X basis. And that is a first order perturbative process. It's just degenerate perturbation theory. It's fast, so you can do it with realistic numbers in a few hundred nanoseconds, which is actually faster than IBM's 2-qubit gates on their quantum machines, using their numbers, roughly speaking. And going to this basis might be a really big problem for certain applications of cavity QED, but it actually, for topology, we don't care about basis. So it's perfectly good for a lot of what we would want to do in topological experiments. There are some subtleties, but we think this is probably the best way to go. And then finally, once we have all of this, how are we going to measure it? Well, the nice thing is the bulk is kind of disgusting. It doesn't do anything so easy to see. The edge actually just pumps. Basically, it's a Chern insulator at the edge. So it just pumps from one photon to the other at a quantized rate, which you can think of as the Hall conductance. So you just prepare one of the qubits in its ground state, and it pumps into the other, one of the photons into its ground state. Energy gets pumped into the other photon at a quantized rate that you can easily determine. Here's what it looks like until eventually you kind of leave the topological phase and bad things happen. So that would be nice if they could measure everything about the qubit. Probably the easier thing for them to do is to prepare coherent states and measure this thing called the Wigner function, so the semi-classical distribution of the photon. And what happens then is you get this energy pumping in spiral that basically it's pumping one photon at a time in appropriate units until eventually that also leaves the topological phase and starts to do something a little bit funny. You can start to see it's deviating by this. But these are things that people have measured experimentally, and I want to emphasize is something that we can do now, and I think a much, much more realizable setting. All right, so that's what I want to say about the anomalous Foucault photon pump. There are a lot of, let's say, interesting, deeper questions here, which I won't get too much into unless there are questions. What I want to spend maybe 5 minutes or so saying is what happens when we combine these ideas of transport and non-equilibrium physics with the idea that topological physics is interesting in cavity QED. We think we have something cool, which I've started to call topologically mediated interactions or transport. Oops, that should not be there. Here we go. It's motivated by this experiment, which is from the Simon Schuster. It's mostly Schuster's group, in which they create these superconducting cavities by milling literally cavities in a chunk of aluminum, and then they couple them in this experiment really just at one port to a superconducting transmon qubit. Now, the interesting thing they can do is they can dump a little piece of ferromagnet into some of these cavities that changes the boundary conditions for the electromagnetic field. Basically creates a flux there on the sites. And what you can show is that the photons that are hopping around these superconducting cells, they experience what is effectively a quarter flux Hofstadter loss. Topological churning. And they measured that. It has a band structure that looks something like that, crucially with some chiral edge modes.
So is that an actual device?
Is an
5 by
actual
5?
device. 5 by 5 is an actual device. I don't think there's fundamental reasons they couldn't go beyond that. But 5 by 5 is where they're at, expect. But it's precisely a picture from this picture.
Yeah.
And they've done spectroscopy to show kind of there's some stuff sitting in the gap. You shouldn't overread it, but there are what appear to be edge states and what appear to be continuous. So the question that we wanted to ask is if you can get these interesting topological edge modes in superconducting resonators, what happens if you then couple a pair of qubits to the edge? Do these chiral edge modes actually mediate interactions between the two qubits? And if so, what are its properties? So where we're going to do that is we will imagine coupling two qubits into this lattice. We'll park them at some frequency that's in the bulk gap of the edge modes. We'll couple them in by just tunnel coupling with a identical strength G, though that's not super important, but maybe identical. And we're basically going to ask within the single excitation manifold, if I start off with this qubit excited, what happens? How does it emit photons into the lattice, and how do those photons get absorbed by the other? So this, you can kind of make a very easy prediction here, right? These are chiral edge modes. They keep going forever at a finite velocity. What should happen is you get infinite range interactions, right? This guy emits a virtual photon, it gets absorbed by the other guy, and then back and forth. You can go through the perturbative calculation to estimate the frequency of these oscillations induced by the coupling. And there are a few things to notice here. The one, probably most important one, is that it depends very sensitively on how close you are to the nearest levels. This is very much like an RKKY interaction in too few dimensions. So in 2D, it's a reasonably convergent thing. In 1D, which is what we have here, there's a lot of divergence in the denominator, which if you then treat it as an actual sum in a finite system, gives you kind of a 1 over sine of the distance to the nearest energy state in units at the level space A. But other than that, you definitely get long range interactions, and it looks like it should behave well, and that's what we see. We do this numerical experiment, you get long range interactions with high fidelity. This little bit of tuning of the frequency of the qubits relative to the finite frequencies of the modes of the edge modes gives you very, very large tunability of the frequency of these oscillations. So the x-axis here is the same. All I'm doing is I'm tuning epsilon by a little bit, and you're seeing that 1 over sine behavior can really modify the frequency a lot within the perturbative calculation. You can map it out. You can see the perturbative theory works pretty well at reasonable system sizes. The first surprise for us was fidelity of oscillations, which kind of, it looks a little bit funny. It looks something like this. It's high fidelity oscillations away from the resonances, and then near, we got a number that said 0.75. So I should say that's not actually 0.75. What's actually happening is on resonance, you're getting slightly different behavior. Because now you can take that one edge mode that you're resonant with plus the 2 qubit modes. You can just do degenerate perturbation 3 at 3 levels, and you actually get 100% fidelity oscillations mediated by a non-virtual photon. And then if you time average the probability of being in one of these qubits, that's where the 0.75 number comes from. So it's a slightly different behavior. It doesn't satisfy this equation, but it gives you a sense that near resonance, something interesting happens. Away from resonance, something interesting happens. In between, what we want is some control. So that's what my student Boris has been working quite hard on, is to try to come up with a better control over this, somewhere that's wishy-washy. Is it right near a resonance or not? And to try to come up with a way to make this more robust to that really, really fine-tuned energy shift that's sitting in the denominator there that we don't want. Also to ask how strongly we can couple these before we lose any control at all. So he came up with what I thought was a very nice technique, which is to basically just look near one of the qubits, write down the Schrodinger equation. This is a single particle equation because we're in a single particle manifold. And what you can do is you can separate it into a bunch of stuff that happens related to the qubit, and something that actually only depends on the bulk quantities, assuming that I knew the eigenvalue lambda. And then, if I isolate all that just bulk dependent stuff on the right-hand side of the equation, that doesn't depend in any way on how strongly coupled I am to the qubit. So what I can do is I can solve that side of the equation by just going to the deep, deep, deep perturbative limit. G goes to 0, get a full functional dependence on lambda, and then I just solve this equation for arbitrary G. And it works. I mean, it works beautifully. So here's the perturbative case. These inverse sine functions become those guys. The slope of this line is about kind of the left-hand side of the equation, the lambda minus lambda times G squared. And as I go up in G, the slope of that red line is going to go down. And you still get the exact solutions as kind of the intercepts between these two curves. And I think I didn't include it, but you can go to G equals 1,000 and you get the right answer. It's an exact solution as long as you only care about the, well, edge modes. So the nice thing here is we know exactly what these functions look like. They're determined by the edge modes. And so we have now an almost exact analytical solution for the frequencies of the modes, and from that we can probably massage it into something like the fidelity of oscillations. So Boris went through that calculation. It allows us to write down a scaling theory of these oscillations, and what we find is that the relevant quantity is G squared times L. So G squared needs to be rescaled by 1 over the linear system size in order to get a well-defined thermodynamic limit. And your oscillation frequency is in units of the level spacing, probably not surprisingly. But then we can show this works, and we can show that as you go up to stronger and stronger coupling, the difference in the frequency of oscillations between, let's say, very close to resonance and very far from resonance gets narrower and narrower. So it's very wide here, but it gets narrower and narrower as you go up to strong coupling, meaning that it's a much more robust protocol. So we've tested that, and we've also shown that this works for the fidelity. So you have a similar scaling form for fidelity. This is the data I showed you earlier. This is data now at stronger coupling, G squared times L to the order 2. On the one hand, your fidelity is no longer 100%. It's about 30%, but there's a finite fidelity despite this lattice. And now the fidelity and the oscillation frequency is very insensitive to how close you are to the resonances, which we think will be potentially useful experimentally for actually making this. So to quickly summarize, the flash of data that I've shown here, chiral edge states allow you to mediate infinite range interactions in this churn insulator. You could do the same thing in 0D. That's exactly what's done in cavity QED. To my mind, that's nice, but it doesn't allow you to do much engineering. So for example, edge modes can be used to route signals from here to there. You can't do that in 0D, it's just one cavity. If you go to higher dimensions, 2 or 3D, you get decaying interactions. So the infinite range nature here is special to 1 dimensions or below. You could do just 1D systems that are not chiral edge modes. And that actually does behave quite similarly if it's 3 particles in 1D. There's a little bit, which is now you have left movers and right movers, so they can destructively interfere when they meet at the second qubit. So you get some spatial dependence associated with that. But probably the more important thing is Anderson localization will kill these 1-dimensional edge modes that
Are these interactions directional in the sense that particle 1 can influence 2, but not vice versa because of the chiral nature of it?
No, because This is summed over many loops around the lattice. So the frequency scale there is still small relative to kind of the time that it takes for a photon to propagate from here to there. It has to propagate from here and then back. And so there's a chirality associated with essentially the phase of the interaction between the two is something like e to the I times the distance divided by the circumference, 2 pi I times that. So there's a phase associated with the interaction, but the magnitude doesn't depend on it. And there's no other, I don't know, form of chirality. That's, and then in 1D, it legitimately destructively interferes. So the amplitude itself depends on the distance between the qubits. Yeah, probably the worst thing is that 1D non-chiral edge modes will localize, and that will now give you no long-range interactions. Whereas the nice thing about topology is it's incredibly robust. So pretty much anything you do that doesn't close the topological phase transition, this scheme should still work. All right. And so that's what I wanted to say today. There are a lot of other interesting things that we're studying in this kind of context, and these flash through these. Those are the 4 things I'd be happy to talk about later if you like. In summary, we've shown that cavity QED and many-body cavity QED is both very interesting for non-equilibrium physics and many-body physics, but also for topological physics is a very natural connection to flow-K topology. And if you think of topological cavities, they can do something quite interesting to those many-body platforms as well. So with that, let me thank my students, Mancho, who led the first project along with Saeed and Mohsen, and Boris, who led the second project. And I'm sorry, I forgot to highlight him along the way while we started that project. This was funded by the Welch Foundation, NSF, and some money from UT Dallas directly. And with that, thank you. Happy to take more questions.
No questions?
In the outlook, the last one, I want to ask the quantum sensor, what
Yeah, so
What
this
is
is
the-
something that has been so far a vague, but hopefully not too long a vague discussion with Gil, Raphael. Not so much our topological system, but the simpler one. So the dimensional reduction of a Chern insulator is a single qubit with 2 incommensurate photons. These are known to pump from one photon to the other at a rate that's effectively the quantum Hall pumping response. What we managed to convince ourselves is that if you take one of these, turn it into a classical drive, so you're classically driving a qubit, and then you're weakly putting in a second photon. Essentially what should happen is, depending on the initial state of the system, because it's a Chern insulator, so it depends on which band you're in, depending on which state you have of your qubit, the monitored state of the second photon out here should kind of topologically branch and give you a topological sense of the state of the qubit. And back of the envelope, the sensitivity of this sensor is actually very high. It's comparable to a lot of the other superconducting qubit measurements today. We actually don't even have to worry too much about topology. All you need is that the amount of photons that go through basically depends on the initial state of the qubit, as long as you know what that mapping is. And so we're trying to clean that up and make an argument that basically this could be a way of measuring the qubit state. It's fairly robust and inherits all the usual topology stuff. Yeah.
All right. Thank Mike again. You might be around until 5-ish.
5-ish.
Go for a walk. All right.
Around 7.